Let's try this out with the function that you've been working on the whole period. The function rule there is actually 1 minus x to the power 4. With x going from minus 1 to 1, and increments of 0.1, and y going from 0 up to 1 with increments of 0.1. That graph should look familiar, because that's actually the function I used for the handout tonight. And we did right-hand endpoints. Now we approximated the heights, right? So we may not get exactly the same thing, but we have done it with right-hand endpoints with 4 subintervals. So we know about what that answer ought to be. So that's a good way to test the program. If I hit my program area, and I'm now going to leave it on execute, which is the first thing that it gives me, in all likelihood it won't work because I'm a terrible programmer. And so it almost never works when I first run it. But I hit enter, and that brings up the program. I hit enter again, and lo and behold, it wants to know the left-hand endpoint. Let's tell it -1. And then it wants to know the right-hand endpoint. Let's tell it 1. And then we wanted 4 subintervals, and it tells me 1.4375, and I think that sounds kind of familiar. What did we get here? 1.44. That's pretty strong evidence that the program's actually doing what we think it's going to do. And so if we look at that area with 20 rectangles, this is the beauty of the program is, you know, I said immediately, let's redo it with 5, and then let's try to think about redoing it with 10. Well, with no additional work, I just hit enter again, and it asks me what I want for a left-hand endpoint. Well, that was still -1. The right-hand endpoint is still 1. But now I want 20 rectangles, 1.59334. Now, by the way, the actual answer is 1.6, is the exact area under that curve. So with 20 rectangles, we've got a pretty good estimate of the area. That little bit that we're losing isn't all that bad. Because we have some overage where, you know, the right-hand endpoints, if you look back at this picture, actually, no, we don't have a lot of overage there, do we? We have overage here on the left that was pretty extreme. And so that kind of offsets what's happening on the right because of the symmetry of the curve. But the neat thing here is you can also do something you would never do by hand. You can take a left-hand endpoint of -1, a right-hand endpoint of 1, and instead of 20 rectangles, we could say take 150 rectangles. And it takes it a little bit longer. Now, the exact value is 1.6. So if you take this out to 5 decimal places and then round it, you get something very, very close to 1.6. If you take it out to the 4th decimal place and then round it up 1, it actually gives you 1.6. Yes, sir?
Would it ever go over 1.6 by then, though? So let's say the next one you did 200, and you
Yeah.
did 1.6, and the next one you did 250.
Well, with this particular curve, it won't. But in general, it could. It all depends on the particular properties of the curve. So that's one of the businesses. Is what 5.1 is about this business of approximating areas under curves. There is a particular application of this, just to give you an idea of what an application of this looks like. So here's what an application would look like. Let's focus on just the right-hand side of this picture. And in our application, I want to think of this as being time, going from 0 to 1 second. So my horizontal axis is time in seconds. And this is the curve, y equals v of t. This is the velocity of a car on an air track. I'm not going to worry about the left-hand side over here. Just cross that out. So t going from 0 up to 1. This is the final 1 second. So looking at this as a velocity curve, what's happening to my little car? Okay, its velocity is going down, and at 1 second it actually becomes 0. So it comes to a dead stop at 1 second. So if I go through and think about this idea of rectangles, and I build these rectangles, what's the dimension associated with this, quote, area of the rectangle? The width here is time. The height is velocity in, say, meters per second. What happens when you multiply a rate times a time? Now that's when you take the derivative of velocity. Yeah, what's rate times time? It's distance. If I take meters per second, so this area in here, units are meters per second, that's the height, times seconds, that's equals meters, the distance traveled. And so one application of this idea of area that has nothing to do with area actually is if you have the velocity of an object and can approximate it over time, say by measuring it with a radar gun, you can take that velocity curve, the area under that curve is the total displacement of the car. It's how far the car traveled in that 1 second. And this is your first hint that the distance here, well, velocity and distance are related. Velocity is equal to the derivative with respect to time of the position function, s, where s of t is the position and time t. So somehow when you take the derivative function, the velocity, and you find this area under the curve, it has something to do with the original function that the velocity is a derivative of. And this kind of foreshadows the idea that what we're doing now might come back to have something to do with the derivative stuff that we've been doing all semester long.